Hey, and welcome, and thanks for coming along to the combined Brisbane, Melbourne, Sydney data engineering meetup. This is like the Voltron of meetups where everyone combines together to become the super meetup. And I just wanted to say thank you for coming along tonight, and a big appreciation for everyone who's joining us remotely, and especially to our presenters tonight. So we've got a fantastic couple of speakers tonight. Just to keep this community together and make sure that this event goes smoothly, we've got several ways that you can both follow along and participate. The best way to follow along is either as you have joined into the meetup group, you can also follow along in Twitch. The way that we want to encourage participation is we'd love to hear your questions and feedback. And the best way of sharing those questions is either in our Slack channel, through Twitch, or within Zoom itself. So there's several ways that you can, if you've got questions as we're going along, please don't hold back. Please share your questions as we go. But at the end of each presenter's talk, we'll be feeding those questions back to the presenters. So we'll give them the stage and then we'll be sharing the questions afterwards. So Zoom, Data Engineering, Slack, and Twitch are the best ways to interact with our community as we're going along tonight. Before we kick off, I did want to do an extremely quick shout out for Data Engineering Bytes. That's a fantastic community conference event that we've got on the 20th and 21st of August. Leo's going to give a bit more of a presentation for that later on tonight. But I just wanted to put that out as a bit of a teaser, just to make sure that you've got this on your calendar. Data Engineering Bytes is going to be a fantastic community event, and really want everyone to get involved. If you love what you're hearing tonight, you're really going to love Data Engineering Bytes. So I'm Simon Aubrey. I'm the co-host for this meetup in conjunction with Peter Hannes, who helps out from the Sydney team. And we've got a whole bunch of great helpers. But tonight, really wanted to pass the stage over to our two fantastic presenters. So we're going to have Graham Polley. He's a software engineer, and he's going to be sharing some fantastic learnings and some learnings from the trenches dealing with GCP. And then we've got Mahdi Askari. He's a solution arc over at Databricks, and he's going to be sharing some really interesting updates, which I'm super interested in, especially some of the summit announcements and some of the enhancements out of Spark 3.0. So I'm really looking forward to both of these presentations tonight. So this is roughly what we're going to be hearing. So very quickly, you don't have to listen to me. I'll be passing over to someone much more eloquent. Graham's going to be sharing some tales around GCP data engineering, essentially some stories from the trenches. Leo's going to be giving us a quick update on Data Engineering Bytes. And then we'll be closing out the evening around 7:15. Mahdi will be giving us a presentation around what's new in Spark 3.0. And with that, I'm super excited to pass over to Graham. So I'm going to ask Graham to take us through tales of GCP data engineering. So I might pass it over to Graham.
Okay, thanks, Simon. I don't know about speaking more eloquently. I am Irish. We can't pronounce our THs. So if I say crazy stuff like 33, please don't snigger. Or if you are going to snigger, go on mute. But anyway. All right, let me see if I can share my screen. Am I sharing my screen? Can someone give me a thumbs up? Looks okay. Cool. Go into presentation mode. Everything okay? Thumbs up, Simon? Yeah? Great. So hi, everybody. My name's Graham Polley. Based down in Melbourne. Hope everyone's keeping well and safe in these trying and challenging times. It's really nice to be here, sharing my experiences with working with Google Cloud. I've been working with Google Cloud Platform for about 6 or 7 years now. Also work on AWS, but doing a lot of data and analytics on GCP. And I've come across some things over the years, certainly around the enterprise, working with some of our customers in there. And I just wanted to share some of those battle scars and tips and tricks for working with like the core tools for data and analytics on GCP, primarily Dataflow and BigQuery. And I'll give a quick introduction to both of those tools. I'm an engineer. I'm not good at slides. I find live demos infinitely more valuable and seeing some code and seeing tools work. So I will whiz through a few slides just to set the scene, and then we'll drop into some live demos. And fingers crossed, I've made my sacrifices to the demo gods today, and it all goes well. It was fine when I tested it last night, so it should be okay. You can catch me on Twitter. I'm quite active on there at Polley. And actually, I'm going to go through my top 10 tips for Dataflow and BigQuery, but I've got a much bigger list. We just don't have time to go through it, and you can get the entire list on my blog, which is polley.dev. And one of the articles I have on there is pro tips for data engineering on GCP. So this is like a condensed version. All right, so I know a lot of this meetup hasn't had a lot of GCP talks. So I'm going to try and give a high-level overview of the data stack on GCP, and then dive into those two core tools. So with that in mind, this is kind of what it looks like on GCP. There's lots of blue hexagons there. Might be a little bit overwhelming, but don't worry. We're not going to go into every single one tonight. As we all know, right? Basic process is capture your data, process it, store it, analyze it, and then use it. On GCP, for capturing the data in real time or streaming, you're going to use something like PubSub, just a big scalable message bus that you can hook up topics and subscriptions to and consume that data. Ignore the other three. We'll just look at PubSub, and then for processing that data, you'd use a tool like Cloud Dataflow, which is based on Apache Beam open source. Apache Beam is the development of two products that Google built internally called Flume and Millwheel. They open sourced it about 2 or 3 years ago, which is now Apache Beam. And I'll show how all that wires up and works a bit later on. There's also Cloud Data Prep in the process column. Funnily enough, Data Prep actually just generates Cloud Dataflow pipelines for you under the hood. You get a nice GUI, so it's pointy, clicky. If you don't want to write code, it will just generate those pipelines for you. Personally, I prefer dropping down into code and having more control of the pipelines. But look, if it does suit some businesses, if they want to graphically wire up some ETL pipelines, they can use Data Prep. Just a call out on that. It's not actually a native Google tool. It's a trifactor tool, so you do need to accept their terms and conditions, which is you need to give trifactor access to your GCS buckets and BigQuery buckets, data sets. So just watch out for that. Sometimes that freaks your security teams out in the enterprise. And then moving on to store, Google Cloud Storage, it's blob storage. It's like S3 on AWS or blob storage on Azure. Nothing too much to talk about there. It's very scalable. It's the glue. I see it as the glue that kind of holds everything together on GCP. You can't use BigQuery without cloud storage. You can't use Dataflow without cloud storage. You can't use Bigtable without cloud storage. It underpins all of the data tools on the stack. Then BigQuery is in both. It's in storing and analyzing. I'm going to move pretty quick through these slides, but we will go into a little bit more details on Dataflow and BigQuery. I call BigQuery SQL as a service. It's shovel your data into it, write SQL to get insights. That's pretty much it. It's a massively scalable data warehouse. The architecture is a complete separation of storage and compute. So Google are able to scale both independently. It runs on a petabit network. I've seen some stats being thrown around by the BigQuery team. They can shuffle about 1 terabyte of data a second across that network. And I've worked on some pretty large scale projects where we were able to hit 10 terabytes in about 20 seconds and was able to do multiple aggregations and joins and predicate filters. And it's probably one of my favorite tools on the stack. I do enjoy working with BigQuery. Analyze BigQuery, we just talked about that. SQL as a service. Bigtable is a NoSQL service, massively scalable again, compatible with HBase. You'd probably only be using Bigtable for data volumes 1 terabyte or above. Runs a big cluster under the hood, massive throughput, like single-digit millisecond latency on Bigtable. So if you're doing like any time series analysis, that's probably a good tool for that. I've just noticed there is one tool missing off this, which is Cloud Spanner, but I'll have to update those slides. And then use, right, you just plug in a BI tool, whatever BI tool you want to use. And then for orchestration, yeah, Data Fusion is a relatively new tool on the stack. It's based on CDAP. It's managed CDAP, think of it like that. It runs on a big GKE cluster of 3 nodes. It's kind of beefy, enterprise grade, but it's got lots and lots of connectors and syncs. And it's, again, a pointy, clicky GUI. Data catalog, data governance, who needs it? Cloud Composer is managed Airflow for orchestration. Again, runs on a big beefy GKE cluster. I personally have been using another tool on the stack for orchestration called Cloud Build. I'm a big fan of, again, should probably play this slide, big fan of Cloud Build. It's cheapest chips, it's serverless, it's ephemeral Docker containers, running your build pipelines and CI/CD, and you can do orchestration in it, and it has auth baked into it, and I really like it. So that's kind of the main tools on the stack on GCP for data, and we're gonna zone in now on PubSub, Dataflow, and BigQuery. It's really weird talking on a webinar. You don't get the feedback from the audience. Anyway, hopefully I'm going okay. I haven't said 33 yet, which is a good thing. These are your classic patterns on GCP for ingestion of data and getting it into something like BigQuery, which is again, SQL as a service. Classic batch and streaming. So if we look at the batch pattern, I've just got a poll pop up. Are you using Google Cloud? I'm going to close that because clearly I am. Yeah, flat files, drop them into cloud storage, which is like S3 equivalent. I personally like to have a cloud function hanging off that. That's like an AWS Lambda, which gets triggered when the file lands. There's actually, it's not shown in this diagram, there's 2 ways to load that data into BigQuery. You could go straight from that cloud function to call the BigQuery load API, and it just loads it in for free from GCS. So think JSON files coming in, or gzip, CSV, whatever, Avro, whatever files you're sucking in. There's a bit of a caveat with that, which is the runtime or the maximum execution time of a cloud function is 15 minutes. Now that's fine if you kick off a load job in BigQuery, which is asynchronous, but of course you want to be polling that job and you want to check that it was successful. So if you run over 15 minutes, your cloud function is going to die and you won't have a hook back into the job to check if it failed or not. And if it failed, you'll never know. So if you're loading lots and lots of small files like micro batching, fine. Just go straight from a cloud function to BigQuery, works. But if you're doing anything at a larger scale, I like to put Dataflow in the middle, which is a massively scalable ETL service on BigQuery, on GCP. And again, we'll jump into that in a bit more detail. So we'll go file into GCS, triggers a little cloud function. All that cloud function does, it stitches together GCS and Dataflow and says, hey, Dataflow, a file has landed. Please load it in, spin up a cluster, read it, dump it into BigQuery. For streaming, classic IoT or capturing logs at massive scale, dump it into PubSub, huge message bus. Dataflow can do both. These polls keep popping up. Is there any way to, I don't know if you can turn off the polls for the presenter, Simon? It'd be good if you could. PubSub, Dataflow can actually work in batch and streaming mode. So you can pretty much follow it's an opinionated framework, the Apache Beam API, but you can hook it up to do batch ingestion, and you can hook it up to do streaming ingestion, which is quite nice. You just use the same framework for both. So you can use Dataflow hooked up to PubSub. That's just got a subscription under the hood, and it's just reading all the events off the bus. And as they're coming in, it's hitting BigQuery's streaming API. So BigQuery does have a streaming API. So they're your classic patterns for ingestion on GCP. And apologies in advance if you hear little kids running around. It's dinner time. I've got a 1-year-old and a 4-year-old, and it's chaos normally at this time. So, okay. have a little look at Cloud Dataflow. What is it? Like I said, you can do batch and streaming using the same API. That's quite nice. And you use the Dataflow SDK, which is now the Apache Beam. So it's all underpinned by Apache Beam. You can go to the Apache Beam website and have a look at it. It's all on GitHub. I personally get involved in that, issue some pull requests and so on. They never get accepted because my code is awful. But the sell of Apache Beam is you can write the same pipeline and run it on a multitude of runners. Well, a multitude is a bit of an embellishment. There's 4. But you can write your pipeline, you can run it on Flink, you can run it on Spark, you can run it locally using the direct runner, or as Google would like you to do, you can run it on Google Cloud, because that's where they're going to make their money. So it's Apache, think of Cloud Dataflow as managed Apache Beam pipelines on Google Cloud. So what actually happens is you write your pipeline, you submit it to the Dataflow service, Dataflow takes your pipeline, constructs a DAG, it then spins up a worker pool or a cluster running Docker. It packages up your pipeline, it distributes it across the cluster, it then starts reading the source of data in, it scales it automatically, it has fault tolerance built in, it auto scales up and down, it has logging all baked into it, so it's a fully managed service. And that's pretty much what it is. But you can also take that same pipeline, change the runner to be the local runner for development, say, and it will just work without changing any code. And the same for Spark and Flink. That said, I don't have a lot of experience working with the Flink and Spark runners. I have heard good things about them, but I primarily work with the Dataflow runner, which is running my Apache Beam pipelines on Google Cloud. Okay, so there's a few languages you can write your Apache Beam pipelines in. There's Java, which is, in my honest opinion, that's the most mature of the SDKs. It also has good feature parity with the Dataflow service on GCP. Python is good. It's catching up to Java in terms of maturity and feature parity. And then there's also Go, which I would recommend not using just yet. It's not ready. It is, yeah. Don't use it in production. Play with it in dev if you want to, but if you're going to go production, go Java. If you're really anti-Java and you can't stand all the boilerplate code that comes with Java, well, I've been experimenting with Kotlin. You could write in Kotlin, but you could drop down into Python. Just bear in mind there are a few little features of the Dataflow service on GCP that are not supported by the Python SDK. Just worth noting that. So that's pretty much it, right? Write your model and then run it across any of those runners, Flink, Spark, Google Cloud, Dataflow, and local. So, like I said at the very start, I've got a blog with lots, and I just keep curating it and keeping it up to date as I come across these gnarly little engineering caveats that I come across in my day job. But these are my top 10 for Dataflow and BigQuery. This is a classic. I see it all the time. When people start using Dataflow, they don't use the local runner for development. So they're just getting used to Dataflow. They're figuring out how the API works. They're figuring out how the libraries work. And instead of using the local runner, which just obviously runs locally on the machine, your dev machine, they run it on Google Cloud, which spins up clusters, which consumes quite a bit of money, and then you get bill shock. So watch out for that. If you're going to go and experiment with Apache Beam and Dataflow, absolutely use the direct runner, not the Dataflow runner, until you're ready to shake that pipeline out on GCP, and then you would start using the actual services on GCP. We briefly touched on that, so I can skip over it. It has 3 SDKs. My recommendation is Java where possible. If not, drop down into Python. Hesitation around Go, just be cautious. It's not very mature. They being the Apache Beam team / Google, announced a new feature called Beam SQL. It's based on, I assume there'll be some people on the call who would know what Apache Calcite is. Look, it's promising. I've been testing it. It looks really good. It's just very narrow at the moment. in terms of some SQL functions aren't available. It falls over as soon as you start using some more advanced SQL within your pipeline. But essentially what it allows you to do, it allows you, instead of writing code for your pipeline, you just inject SQL into it, and the service will generate the DAG for you based on your SQL. It's one to watch out for and keep an eye on, but again, I wouldn't use it in production just yet. I have seen that mistake made. It was rolled out to a production system. And it had to be rolled back. Yeah, this is a good one. So if you're doing streaming pipelines into Google Cloud, and the classic pattern which we looked at the very start, which is pub/sub to Dataflow to BigQuery, there's two ways to get that data into BigQuery. You can hit BigQuery's streaming API directly. However, that comes at a cost because there is a charge for hitting the streaming API into BigQuery. And it might not be important at lower, when you're not at the terabyte scale, but if you're pushing some serious data through those pipes, that becomes a significant cost. So one tip you can do to get around that, you can drop down into micro batching directly from Dataflow. And I can show you in code what that looks like. But basically, you tell Dataflow not to hit BigQuery streaming API, even though it's sucking that data off the pub subtopic. And what it does is you tell it to do file loads, and it will intermittently write. You set the trigger on how, or the frequency on how often to write the files to GCS, and it basically micro batches it for you under the hood. So it writes the data to files in GCS and then just loads them into BigQuery. Obviously, there's trade-offs. You won't have your data as fast as what you would have with the streaming API, but you save some money because loads in from GCS are free in BigQuery. So if you are cost sensitive, have a look at that. This is a classic. Dataflow is a fully managed service. We all know working with cloud, things can quickly get away from you, costs can get away from you because it's really easy to spin stuff up, right? It's a double-edged sword. And Dataflow, if you don't specify the instance type, it will pick a pretty big VM to run in your worker pool, and that could scale up to 20 VMs. I always like to drop it down to the min size and then experiment with the pipeline first before deploying it. So watch out for that one as well. Again, this is very costs. Sorry, Dataflow does have auto scaling built in. If you don't put a cap on the number of instances, it will just happily scale and scale and scale until you've got 50 VMs in a worker pool, and that's going to get pricey. It's good and bad, right? If you're working at massive scale, it's great to have the ability to scale like that. But I have seen it sometimes scale for not for no reason, but I'm a bit dubious. I have some hesitations around its auto scaling algorithm. So I let it scale, but I always cap it at, say, 10 workers. And if it does need to go through 10 workers, then we'll do a new deployment and we'll bump that up to 5. But I'll never just leave that uncapped so it can scale to 50 or 100 VMs. So it's going to cost you a lot of money. This is a relatively new one. Google have rolled out a new version of their GCE. It would be like EC2 on AWS VMs, which is what Dataflow is using under the hood, just using GCE for the compute and writing all your data to BigQuery or Bigtable or whatever that is. There's a new generation now of GCE instances. It's just newer hardware, new CPU architecture. It's called the N2 class. More expensive to run per hour, but obviously you get a massive performance boost with them, which could potentially lead to savings, right? Because you don't need as many workers in the worker pool processing your data anymore. So instead of 5, maybe only 2. Yes, they're more expensive per unit, but the overall cost comes down and you get a boost in performance. The default for Dataflow is to pick the N1 class, which is the older generation. I've been doing some benchmarking and experiment with N2 and would definitely recommend having a look at it. You can update your Dataflow streaming pipeline on the fly with new changes. Just watch out for Google will do a compatibility check when you upload your new code. If it fails the compatibility check, it will say computer says no, and it won't do it. So you need to have a strategy in place to drain that pipeline, tear it down and bring a new pipeline up without having any downtime to your upstream or downstream system. So that does catch a few people out. Another classic, keep your security teams happy. By default, all the workers in the worker pool will have public IPs. If you don't need to be making calls out on the internet or wherever to an API, just turn them off. There's no point having them. It's a simple flag, dash use public IPs, false, Boolean flag, done. Yep. This is an interesting one. Dataflow, like a lot of the tools on GCP, uses GCS under the hood. So when it's sucking in data, it's writing to GCS, and it's storing intermediate state on the pipeline on GCS, and it's putting a lot of data in GCS. And what we found working with it, it wouldn't, when the pipeline would be finished, like batch pipeline, it would run for a few hours and it tears itself down. You don't need to tear it down. It would leave all these files in GCS, and we noticed then all of a sudden our bills were getting higher and higher, and we were like, oh, where's all these? Why are we getting so many costs coming from GCS? And it turned out it was Dataflow not deleting the files. I reported it as an issue a while ago. It was fixed, but I think there was a regression bug. It came back in. I still see it pop up occasionally. My tip here is to always err on the side of caution and just have a post-processing step. It could be as simple as a batch script that just goes to GCS, checks it, deletes it, done. All right, I'm probably running out of time for a live demo, so I'll move a bit quicker. Apologies. Where are we? BigQuery. Yeah, one of my favorite tools in the stack for working with data. Separation of storage, compute. Lots of hardware, big petabit network, chuck data at it, write SQL, and it scales. It just elastically scales. This is the architecture of it. I won't go into too much detail on it. You can read about this in the white papers. Obviously, Dremel was the white paper. Sorry. Google built Dremel internally. BigQuery, think of Dremel as Google's internal BigQuery, and BigQuery is what we see publicly. But under the hood, it's the same architecture. It's columnar, so they can scale it much better and get much better compression ratios on the storage system. It runs on Jupyter, which is Google's custom-built petabit network. I think I said at the start, it can move about a petabyte a second across that network. It runs on Borg, which is their container management system, which is what they built 10 years ago. And then we see GKE. So they just scale containers for compute. And then the storage layer is Colossus, which is the next generation of GFS. And Colossus, think of that as tens of thousands of SSD disks sitting on top of that petabit network. So BigQuery, once a query comes in, it's the execution engine. Goes, okay, where's my data? Goes out, farms it out to Colossus, pulls all that data back in over that network, and then shoves it into RAM, churns it up, and gives you your answer. Okay, so BigQuery top tips. Export all your audit logs and billing logs back to BigQuery. That's a really nice one to do, especially in the enterprise. There's a simple trick with your logging. You just check a box and all those logs will go, because the default retention periods on logs in GCP are like 30 days. You can override that now. But I like to just push it back all into BigQuery, and then you can just write SQL to analyze data activity, audit trails, and so on. It's a nice little pattern. It is true that BigQuery likes really wide denormalized data structures with nested and repeating data. That is not to say you can't have normalized structures like star schemas. You can. BigQuery just performs better on denormalized data structures, and that's due to the architecture of it, running separation of storage compute on a distributed system and columnar storage. Right? It just likes big, fat, wide tables, and that depends on your use case, depends on what you're working with. I like to have big, wide, denormalized tables. I think it's easier to write SQL for that. Some people argue, well, you're doubling up your data, but the cost of storage is so cheap on cloud now, it's negligible, right? So, look, as with everything, trade-offs, and pick the best tool for the job or best pattern for you. BigQuery charges by the terabyte scanned if you're on, there's two pricing models, on demand and flat rate. I won't talk too much about flat rate. That's like real enterprise grade. You just pay a flat fee per month. On demand is normally what people are working with. You get charged per terabyte. It's currently $5 US per terabyte. Depending on the columns that you put in your SQL, it will scan that data. If you do a select star, you're going to scan the entire table and get charged for a full table scan, because BigQuery always does a full table scan. The keyword limit in your SQL, if you do a select star from table limit 100, you will still get charged for a full table scan, even if you do a limit 100. The only exception to that is if your table is clustered, but don't have time to go into clustering. Clustering is just a performance boost to your SQL queries by Google will co-locate your data on disk and order it under the hood, so less data to scan and so on and faster. And there's no indexes in BigQuery, by the way. You don't define any indexes. For partition tables, enforce, you can set a require partition filter to be true, which forces any downstream consumers or analysts who want to read that table, they have to use a where clause using the partition column, and that will reduce costs and also give you a performance boost. BigQuery recently rolled out materialized views. I'm not a huge fan yet. Still quite narrow. You can't do any joins, for example, so it's quite limited. I think they've still got a way to go until they get to a point where we can be excited about them, and they will get there. I've seen the roadmap for it, but they're just not there yet. But watch this space. Oh, that was 6. Yeah. This is more when you're working in enterprise. There are some third-party plugins and tools that you can use for working with BigQuery. One of them's, just watch out for them because you have to elevate. They require elevated permissions. They're not native tools, and that's fine if you're kind of doing home hobby projects or small organizations. But when you're scaling across an enterprise with big security teams and privacy teams and working with some pretty sensitive data with PII and data sovereignty, it just gets a bit, I would definitely look at the terms and conditions before you accept them and use any of those third-party plugins. And some of their claims are a bit lofty, don't quite pass my sniff test. When they say they can 10x your query performance, I'd rather just try and make my SQL better myself. Anyway, BigQuery is not limitless. Ignore the marketing slides that you might see around. It is massively scalable. I've seen it scale to petabytes. We recently worked on a project where we were working with half a petabyte and just scaled. But it is absolutely not limitless. You need to be wary of data skews, too many joins, ordering. If you do an order, BigQuery has to shuffle all that data across the network. Yes, it's a big fat network and big fat pipes and it can do it, but it needs to shuffle it all across the network into one final node to do the order by and performance. So it's not limitless. Great job, but not limitless. I think I said this. Don't do a select star to preview any data because you get charged for a full table scan. Dataflow is a good tool for doing ETL, but BigQuery itself is actually a good tool for doing ETL. You can do federated queries from BigQuery directly to GCS, so it can read files in. We're doing a lot of work now with DBT. BigQuery. I like using an ELT pattern with BigQuery. So getting your data in and then just smashing it with SQL, which is what DBT is doing, right? Does the T in ELT. Because what I like about that, you just stay in SQL world and you just scale on BigQuery, and that's really nice. So if you're working with BigQuery, certainly have a look at using an ELT pattern rather than ETL. And there's limits and quotas. It kind of ties back to point 7, which is not limitless. And there's a big list on the official documentation. To give an example, the maximum load size per job is 15 terabytes. You can only extract 10 terabytes at a time into GCS. All these quotas and limits. So that catches people out sometimes. They go to build something and they hit a quota or limit. And they go, oh, why isn't it working? And it's quota limit. And that said, if you're a big enough customer, a lot of them are soft limits, as with everything on cloud. If you're spending enough money with them, talk to your account exec or account rep, and they can get them lifted. We have had that happen on some pretty large scale projects. All right, I've bored you enough with slides. Let's have a look at something a bit more interesting. Drop out of that. How am I doing for time? 6:04. I don't even know what time I started on.
You're fine, Graham. Keep going. Everyone loves a demo.
How much time I got left?
How much do you want? 5 to 10 minutes?
Yeah, I probably need another 5. Yeah, 5-ish minutes. All right. Shared the wrong screen. Sorry, folks. Let me just get my screen back. Okay, zoom in a bit. No, I won't, because Zooming's not working. Yeah, there we go. Can everyone see my screen? Someone give me a thumbs up. Peter?
Yep.
Yep, cool. This is BigQuery. I'm using the console just to demo it. Obviously, there's a full REST API behind this. So you can programmatically interact with it, automate it, CI/CD, but just to give you a flavor of it. Data sets over on the left, your query window here in the middle, and then your results in the bottom. I've written some very basic SQL because I don't really know how to write SQL. I'm not very good at it, but you get the idea. It's hitting a public data set, which is all the Wikipedia page views stored in BigQuery. They ingest that data, and you can use it for benchmarking. Simple predicate filter, looking for all articles with Melbourne and title, doing a simple aggregation group by the title and language, and then doing a final order by to make it work hard and shuffle the data across the network onto a single node. I've got different sizes of tables. Let's start with 1 million results. Sorry, 1 million rows in the table. And remember, BigQuery always does a full table scan unless it's partitioned or clustered. These tables are not partitioned or clustered. So I'm going to turn off caching to show we're not cheating. Run that. And BigQuery is non-deterministic, so you won't get linear results in your queries, and you won't get like double-digit latency. It's like seconds for BigQuery, but it's OLAP workloads. You're not going to be using BigQuery for OLTP workloads or low latency stuff. So that did, let's have a look at the table. There's 1.2 million in that, 1.2 million rows in that table, 86 meg. It did a full table scan, did it in whatever that was, I've lost it now, 1.6 seconds. To make it a bit more interesting, let's do 1 billion rows. So if you go there, so 1.2 billion rows, 84 gig, run that. Awkward silence as it runs. Sorry for the baby crying in the background. All right, so it did 1 billion rows in 9.6. Let's make it a little bit more interesting. Let's go to 10 billion, which I think is half a terabyte, if I'm not mistaken. So I'm from Melbourne, so sorry, I put Melbourne in as the filter. Again, awkward silence. We're doing 1 billion rows and half a terabyte. Okay, 19.7, yeah, almost half a terabyte. But let's do 6 terabytes. So it's 100 billion rows. Show I'm not cheating. I'll drop into that table. 106 billion, 770 million, 465,660. The full table is 6.76 terabytes. I'm getting charged 4.1 terabytes, and that's because I'm not accessing all the columns. Remember I talked about at the start, you get charged for the data that you scan when you're on demand. And because I'm not accessing all the columns, BigQuery is smart enough to work out, well, I don't need to charge them for every single column. I can hop across those columns, and I can only charge them for what they're accessing. So this is 4.1 terabytes. This will take a little bit longer. It's 4 terabytes. So let's just see how that goes. It's so awkward doing a webinar and not being able to, like, certainly especially in these awkward silent moments where we're waiting for demos. There we go. 22.7 seconds for 4 terabytes and 106 billion rows. Kind of cool. All right, let's stop that. Let's have a look at some code. Who doesn't love a bit of code? Well, yeah. Wait to see my code, and you might run. But anyway, Peter, screen, IntelliJ, all good?
Yep.
Okay, cool. So I've written a little demo pipeline to show you all tonight. There's 2 pipelines. One is a streaming pipeline, which reads from pub/sub, ingests it, and dumps it into BigQuery. And that's kind of what we're going to show. And then I've written a batch pipeline just to pump some data through those pipes. So it reads 1 billion rows from Google Cloud Storage, flat CSV files, and then shovels them off to pub/sub for the other pipeline to ingest that data. It's just to show its scale, right? And this is Apache Beam. This is what it looks like in Java. Apologies for all the Pythons on the call who are all hissing at me right now. But this is what it looks like. You create these objects called P collections, which is P stands for parallelized across the cluster. So all your data is working. It's a massively parallel what is it? Embarrassing parallel system. I can never remember. Parallelized across the platform, across the cluster. So it's reading from pub sub. It's putting it into buckets of 1 second and then writing it to BigQuery, and it's hitting the BigQuery streaming API. So read, transform, write. And this is what I was talking about earlier. See the streaming inserts? I can change that to file loads to do micro batching, and that's pretty much all there is to it. We'll do streaming because I'm not doing a lot of data, and Google give me free credits anyway, so make them work for that. So that's pretty much the streaming pipeline. That will read at scale from PubSub. A Pardo is a unit of work within an Apache Beam pipeline or within your DAG, which is parallelized across the cluster. When you run this pipeline, your code is basically bundled up. Your class path is scanned, all your dependencies, in this case jar files, if it was Python and so on. The service uploads all those files onto GCP, spins up the cluster with VMs running in the cluster, takes your code and puts it on all the VMs in the code and runs it in parallel. That's pretty much how it works. So my code will be running across the cluster. And we don't need to look at this one too much. This is the batch one in order to pump some data through the pipeline. That's kind of it. This is taking in a pub sub message and returning a table row message for ingestion into BigQuery. I just take it in, set the timestamp, set the payload, and that's it. All right, I can't see my terminal because that little tiny thing in the top from Zoom is blocking it, but okay, I'm gonna guess that Gradle is running. I'm using Gradle as my build tool. Oh, that looked good. So this is gonna deploy the streaming pipeline because I've set streaming to be true in my build.gradle. Yep, cool. So this will now deploy the streaming one. And then once that's up, we'll deploy the batch one, which is, I'm using it as a test to pump data through. So let's see how that goes. So you can see it's scanning the class path, it's getting all my dependencies, all my jar files, it's uploading it to GCP, and then it's spinning up a cluster. So let's actually, while I'm here, because I'm gonna have to drop out of this and go back to my browser. It's all a bit clunky, but I'm gonna change that to false to run the batch pipeline. And here you can see I'm setting the number of workers in the stack, dog fooding my own tips, which is setting the number of workers, setting the instance type to the N2 class. That's all there is to it, right? If I was to drop that to an N1, that's the older generation of VMs in the stack. N2 gives me a newer generation. This is reading from GCS and then writing to PubSub for the pipeline. So let's just kick that one off. Live coding, it's always a bit hairy. Should be okay. Let's make sure that goes okay. So this is now batch one. Java, Gradle, let's go. Come on. Yep, there we go. So it's now deployed the. Okay, sorry, I have to jump to another screen. Apologies for all the jumping around. Okay, you should see my console again. Peter, can you?
Yep.
Cool. So we'll jump over to the Dataflow Console. Here you get it. You get like a full monitoring console of all your jobs running. Refresh that. Yeah, you've got 2 pipelines running. I've spun up the worker stack in Sydney, Australia, which is the only data center Google have currently. They made a blog post recently or announcement that they're opening up a new data center in Melbourne. I think the lights go on in 2021, but for now, Sydney is our only option. You're probably going, hey, Brian, you should say Sydney, but why is it showing Asia Northeast 1? That's actually the metadata orchestrator of the pipeline, currently not available in Sydney. So the VMs and the workers are spinning up in Sydney and processing the data, but the pipeline itself is being orchestrated by the closest point of presence to Sydney, which is Asia Northeast. And that's what's orchestrating the VMs and the pipelines and auto-scaling them, but it's not actually processing the data. So we can actually go here. This is the GCP console for those of you who aren't familiar with GCP. If I go to compute engine, VMs, come on. Yeah, there we go. So here are all my VMs spinning up for Dataflow. And you can see that they're actually in Australia, say East 1A. There's 3 zones, ABC in Sydney. So jumping back to Dataflow, almost there. So let's have a look at the streaming pipeline. So that's the one reading from PubSub, doing a tiny little transformation and then writing it to BigQuery using its streaming API. And you get a nice little graph. Obviously, you can build much more complex pipelines and DAGs. I've just kept it really simple for brevity's sake. And there you go, it's starting to spin up now. It's doing 7,000 elements a second off PubSub. Putting them through a Pardo, so it's converting the base 64 encoded PubSub message into a string for ingestion to BigQuery, and then it's hitting BigQuery's streaming API 12,000 elements a second. You get lots of job metrics. You can see the auto. It's not up yet, but here's the auto scaling history. You can see it scale up to 1, 2, 3 nodes, 4 nodes, and then come back down. You get all these metrics. If we go over to our batch pipeline, which is actually pumping the data into the streaming pipeline. Let's have a look at that. Now that is a complex pipeline, reading from GCS, writing to PubSub, but have a look at the scale it's running. So it's already done 1.9 million elements. Now it's gone to 2 million. It's doing 54,000 elements a second. How many workers does it have in the stack? N1 standard 2 CPUs. So it's doing 5. Yep, you can see it's scaling here. So it's gone, oh wow, I've got to do a bit of work here. There's a billion rows. There's 10 terabytes of data from GCS I need to read. I need more workers. So it's gone yoink, 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 yoink. And it's scaled from, initially it started at, yep, there you go. Current workers 5, and it's scaling up to 10 workers. But the point here is it's fully managed, right? Google just manage all that for you. They just scale the workers up and down. And you get metrics here. And then we jump one more time, almost done. To our streaming pipeline. Come on. It's doing stuff, it's thinking. Yeah, there you go. It's gone up to 28,000 elements a second. Now, that's not currently with 1 worker. If you had 10 workers in the stack, that's 10x that. So it's quite a bit of data you can push through the pipes. Yeah, the show I'm not cheating. This is the final piece of the demo. Hopefully it worked. Should have written it to a new table in here called micro testing batch. I don't see it, so maybe my demo didn't work. Let me refresh the page because there's a bug in the BigQuery UI. Hopefully, we'll see some data in BigQuery. Yay, there's the table. Created July 9th, 6:15 p.m. and it's already got 1.9 million elements, and that's being read in from Dataflow, reading from PubSub, and hitting the streaming API. No, just scale. We can query that table. Interesting enough, BigQuery uses Bigtable under its hood for its streaming ingestion engine. You just don't see it. So when you stream to BigQuery, it's actually hitting Bigtable first, and then Google have a bunch of workers that go out periodically, pull that data from Bigtable, and then shove it into BigQuery. Again, all abstracted from you. It's just a bit of a an interesting tech thing. So if I do a select star from a table, don't do that in production with lots of tables because you get it. This is a complete anti-pattern to what I just told you about 10 minutes ago. There you go. There's the data pumping in. It's all the Wikipedia titles, the article titles. Yeah, and that's it. So hopefully you enjoyed it. Any questions, feel free to reach out. Again, active on Twitter. I love talking about this stuff. Yeah, cool.
I think that was really cool. Graham, I might get Peter to moderate some questions. And if Peter runs out of questions, I've got a whole bunch.
Can I go? Can I go now? That it's. I think I hear my kids calling. Yeah.
There is. Simon, how about you jump in with a few questions? Go for it.
I'll start with a basic question. Firstly, that was super interesting, and I liked hearing all the tales and the areas of watch, especially the ones about limit, which have caused some interesting problems in my past. Anyway, I had a question about Beam. You said there were a whole bunch of languages that were supported, Java, Python, Go, and a whole bunch of runners, sort of Flink and Spark and whatever. Is there a compatibility matrix across these two things, or
Yeah, no, there is. So I could probably share it when I share my slides. If you go to the Apache Beam website, exactly to your point, there's a matrix of all the runners, what's supported, what's not supported, language dependencies, and so on. That does exist on the official Apache Beam website. It's not true. Yeah.
Oh, cool. And just a sort of a hat tip to your question around direct runner. That's a really, really awesome thing. I guess it led me on to a more general question. I know in sort of AWS shops, there's things like local stack for mocking a lot of services. Is there an equivalent of that for dealing with GCP, just the ability to run things up locally and sort of mock the behavior?
There is and there isn't. Some of the services support running locally. For example, if you're writing a Dataflow pipeline, which is talking to pub/sub, that can run locally, but BigQuery has no local emulator. You have to go out across the network and you have to hit the actual service. So it depends. Yeah, it depends on the tool or the service that you're using. And again, there's a list of that on the GCP docs, not on the Beam docs, but which services are supported locally or not. Yeah.
Cool. I might hand over to Peter.
Yeah, I'm a bit of a serverless nut, you know that, Graham. Is Dataflow serverless? Do you have to think about managing scaling yourself, or does GCP do this out of the box for you? Yeah.
They do manage scaling for you, as you probably saw in the demo, right? You saw that stepping up and the auto scaling algorithm kicking in. Obviously, there's VMs running under the hood. Like serverless isn't, we all know serverless is not without some kind of compute under the hood. What serverless is, obviously, is how far that is abstracted away from you and how much you don't need to give a shit about that stuff running under the hood. So Dataflow, yeah, probably put it in the serverless bucket. You write a pipeline, you deploy it, Google spin up all the infrastructure and compute for you. It's all managed. You don't need to do anything with auto scaling. The only things which kind of make me think it's not too serverless, you have to specify the limits and the quotas. You have to specify, you don't have to, but it's good practice to specify the worker types, N1s, N2s. So you do get to turn a few more knobs and pull a few more levers than you would on a normal serverless stack. But yeah, look, it's pretty hands off. You just write your DAG, spin it up, and Google spin up all the infrastructure for you. And same with BigQuery, right? BigQuery is different. Like you don't even see the VMs because there are no VMs on BigQuery. That's all Borg and containers, and that's completely abstracted. So I would actually put BigQuery higher up the stack. Like BigQuery for me is even more SASy than PaaS.
Yeah, no, that's cool. And I guess, you touched on getting yourself into trouble with some of these things, with a bit of bad code pushed to prod, think recursive functions. Can you kind of, get a bit of bill shock going and stuff like that? Or
it's normally my code which causes the problems when I push.
Of course,
that's why
never mind it, obviously.
That's why I've been pushed out to a managerial role. It was not about being a good leader, it's about my awful coder. You just can't have Graham on the tools anymore. But yeah, look, like with any cloud, like with any service, if a fool with a tool is still a fool, right? If you abuse it, if you start spinning up wild clusters with 100 VMs, you're going to pay for it. Literally, right? You will get a big bill. So a lot of the tips are around cost control. We see a lot of that in the work I do.
Yeah. Francisco Liwa, one of our co-organizers from Brisbane, he's asked, do you have experience using Data Fusion pipeline in production? Last question.
I have opinions on Data Fusion. Look, it's very heavyweight. Like, I'm not a huge fan of anything that needs a big GKE cluster under the hood to run. And Data Fusion does. It runs on it. I can see its use case, certainly in the enterprise. And it does have a lot of, and it's based on CDAP, right? And it's got a lot of sources and it's got a lot of syncs, and you can design your pipelines in a graphical user interface. But it's expensive. You have to pay for that GKE cluster with a minimum of 3 nodes. And that it takes half an hour to come up. The other thing with Data Fusion, when you get into problems with your pipelines and you want to start debugging them and troubleshooting them, you get dropped into Hadoop world. So you see Hadoop stack traces, and that's a bit of, oh, really? It's like the whole thing about data fusion, you shouldn't be going down to that level. You're staying at a graphical user interface level, and you're wiring things up. And that's where it gets a bit hairy for me. But to answer the actual question, have I used data fusion in production? No. I've done some analysis on it and evaluations, but we haven't used it yet.
That's, I might have to call time on this. There's actually a whole bunch of additional questions coming through, and I'd love to continue on. So maybe we could continue the conversation on in Slack. And I think because there's so much interest in exploring the GCP space, perhaps we could get Graham on for another.
Yeah, more than happy to. Yeah.
Anyway, Graham, I'll speak on behalf of everyone. I found that super interesting, and I love having demos, so that's particularly cool. So with that, I might pass over to Leo. Leo is going to give us a quick update on all things data engineering bytes. Over to you, Leo.
Okay, thanks, Simon. Yeah, thanks as well, Graham. That was, yeah, awesome demo, and great to hear some of your war stories and insights from GCPs, particularly around, yeah, some of those gotchas. Yeah, hi everyone, my name's Leo. A bit of a background, I'm a data engineer and organizer of DataEngBytes. Yeah, it's awesome to come together tonight, and even though it's virtual, it's, yeah, awesome to be part of this community. So as most of you know, coming up in August, there's an event you're all probably very interested in. It's called DataEngBytes, and it's a community virtual conference focusing on real-world data engineering problems. So yeah, set on Thursday 20th to Friday 21st of August, so right around the corner. It's a two half-day sessions, jam-packed with bite-sized presentations and war stories, yeah, particularly around data engineering. So if you've gotten to this point and you're wondering what on earth it's all about, if the name doesn't give it away, we're sticking to 3 themes. So one of them is data at rest. So you're thinking storage, databases, warehouses, and data lakes. Data in motion. So that's, yeah, all your event streaming, architectures, pipelines, yeah, stuff like Dataflow.
Hey, Leo,
And
do you want to share your slides? Sorry, buddy, to interrupt.
oh, sorry. Thought I was sharing, my bad. Yeah, you didn't miss much. It was just the logo and then our 3 themes. And data in motion, sorry. So yeah, data for machine learning was our 3rd theme. I did want to give a shout out to all of our organizers. Because yeah, without these passionate individuals such as, yeah, Peter Hansen, Simon Albury, yeah, these events can't happen. And yeah, we're all very passionate. We're all some sort of engineer or architect. So yeah, really community-driven event. And also goes without saying, we have a bunch of sponsors that help bring us all together. And without their support, awesome community events like this can't happen. So yeah, like the works of Snowflake, MongoDB, Databricks, AWS, Microsoft Azure, Fivetran, Confluent, ThoughtWorks, Instacluster, Canva, YAO conferences, and Cloud Shuttle. Yeah, quite a few there. And if you're getting to this point and you're wondering, where do I sign up? So you can just visit our website, dataengconf.com.au. All the information's there. The tickets are at an irresistible price of free, so you have no reason not to sign up and come along. And yeah, of course, I'll see you all there, virtually, of course. Thank you.
Oh, thanks for that, Leo. That's fantastic. I can't believe you get all of that goodness for the low price of free. That's amazing. Yeah. So with that excitement still in the room, I think we're going to round out the evening with something I'm really looking forward to. We've got Mahdi, who's going to be giving us a bit of an update on the latest advances in Spark, and specifically some of the new things to look forward to embracing Spark 3.0. So I'm going to pass it over to Mahdi. Thanks very much.
Thanks, Simon. Let me start sharing. Can you hear me and see my screen? Polley, that's not what I want to see you to see, but this one. Can you see the presentation?
Yep, that looks great.
Cool, awesome. Thanks for everyone that stick around. I think it's around 6:30 and spending an extra hour of your evening with us. Thanks for organizer, and I think I enjoyed the topic on the GCP also. My name is Mahdi Askari. As you can see, I'm a solution architect with Databricks. That's my email address, and that's the only place I am. So if anything interesting comes up and you didn't get a chance to ask the question, you want further conversation, feel free to reach out to me on my email. As you can see, the topic is around what's new in Spark 3. I think this is a bit kind of interesting talk, because if you're coming completely fresh to this conversation, not having used Spark, that's probably where you're going to start. So nothing to compare with, but there is a fair bit of community around Spark 1 and Spark 2. Hopefully no one is in Spark 1 anymore, but Spark 2 to Spark 3 translation and some of the new features that I'm going to walk you through it. There are lots of little features here and there, but I picked these 3 categories. The first 2 is performance and usability, and the third one I have one little slide if you want to jump in and start building your code based on the Spark 3, what kind of a version and dependencies that you need. And I'll cover a few features in the performance and usability, but as I said, if you're interested in any of these other features, or you want to have a full list of the 200+ feature, reach out to me. I'm happy to have a conversation with you guys. I thought it'd give you a perspective, what's the work that it went to Spark 3. And I'm going to use the word we in the rest of the slide, and that doesn't necessarily mean Databricks, even though we are heavily involved and still big chunk of the code that goes to the Spark open source comes from Databricks, but this is community effort. So whenever I say we, I actually mean the bigger, wider audience and community that contributed to this. Interestingly, if you notice something that I would like to call out is around 46% of the patches and fixes and features actually went to Spark SQL, and a good chunk of it went to the Spark core. And there's a heavy theme and flavor of improvement on the Spark SQL in the Spark 3.0, which I'll cover a bunch of those things for you. Just a high level view of some of the exciting feature. I'm gonna stay here on this slide if you want to have a quick read. I'm sure we can get the slides out to you guys, so you don't have really to take a screenshot and write anything down. So we'll get the slides out to you. And there's some of the items that I'm going to cover it for you. Specifically, I'm going to cover the adaptive query execution, which is AQE. I'm going to cover dynamic partition pruning, touch on join hints, a little bit around the usability functionality changes that it's not on this slide, and also some around streaming and Python UDFs. So let's jump in and look and see what's happening in Spark 3.0. First, for the performance. AQE, or adaptive query execution. Let's look at a bit of a history on how Spark got to here and what was the steps that we went through to get to this type of execution. So initially, if you use a Spark 1.x, it was pretty much it started all about RDDs, and then initially the data frames were introduced in 2.0. And basically, when you're using a Spark 1, you were having a set of pre-described rules in the engine that those rules were deciding how your code will be executed. The other bit that then we went to the Spark 2.0, and there was a heavy pivot from RDDs to data frame, which still it's one of the things that I ask when I have candidate interviewing for Databricks is, would you pick an RDD or a data frame if you're executing a code and you want to have the best optimization and best runtime? There was this evolution that we went from RDDs to data frames, and we added an extra component in our engine to do planning. So when you were running the query, was 2 extra components, the Catalyst and Catalyst Optimizer and Tangustan started added to this whole different stages of planning for running your query, and we started adding the cost component. So we could predict or calculate what would be the cost of a specific operation, and using that cost component, we could have devised different plans to execute your query. But this didn't really, I mean, it was good. It was definitely, it was a drastic change from Spark 1.x, but still it could have been better, and there was some pitfalls there. something that initially, if you notice that, like, how do we calculate these costs, right? We have to collect the statistics. Those statistics are what we use to calculate those costs and makes decision on how to execute the query. And you will realize that lots of them they're missing, lots of them they're outdated. Statistic collection is very expensive also operation. Then with the separation of compute and the storage, you will have different frameworks or different engines writing to the storage, and then you're using another framework engine to query your data. So the outdated and missing statistics was not really helping to come up with the best way to execute a query. But also, we love SQL and our own lots of subqueries, common table expressions, and we look at SQL queries can be 100 line long and lots of tables and joins. So it was very complex to make a decision before the runtime how to optimize this query for a best performance. And that was basically throwing Spark off, and you come up with this weird, wonderful plan sometimes that you really needed some expert to go in, understand the Spark execution DAG and start optimizing it manually. That was really hard. But also then you had these user-defined functions, so which lots of time you end up like wanting to do something, especially the way that you can define a function in Python and use it in the Spark SQL. It was really handy to write super complex transformation or custom logic in a UDF and then use it in a SQL context. But those were like black boxes. Spark didn't know what's the cost of this UDF. It could have been as simple as adding one, or it could have been like a complex inner join or a for loop or whatever it is. We couldn't know what's the cost of UDF, so we couldn't really optimize any UDF. If I want to go through this, so the next step of this was, okay, now we have set of rules. We can calculate some of the cost of the operation before the query gets executed. But as the query starts executing, we're going to learn more and more and more. Like we have this thing called stages in the Spark query, and each stage, each task in a query execution in your SQL will give us a little bit of a data point that we didn't know before starting to execute. So we thought, okay, it would be a good idea to use those statistics and data that we're going to collect anyway to change the plan during the runtime. So Spark 3.0 AQE actually look at your rules, look at the cost, devise a plan, and use the best optimized plan to execute, but then start collecting statistics and use that statistics, go back and change the execution plan based on the statistics that's been collected. If you see, like this is, again, I said I'll send a slide. I'm probably not going to go through everything, so get some time for questions. This is the typical flow of getting a SQL query and actually executing it and get the result. As you see at the far left, it's the SQL query. At the far right is the RDDs. So everything, even your data frame, eventually gets converted to RDD and runs on RDDs. But how do we get there is around, first we come up with a logical plan. Then we look at our catalog to see whether the tables, the columns, the views that you use in your query, do they exist? So if you get a syntax error that this table or this view doesn't exist, it's exactly at that point. Once we know everything that you need, it exists in our catalog, we come up with a logical plan, and then we do an optimized logical plan, physical plan, then we calculate the cost. We definitely it's guaranteed that we have at least 2 physical plans, and then we apply the cost model and we pick one physical plan to execute. And that's where the execution, the cost model before the physical plan was like the one that chooses the best physical plan to execute. But if you add the execution, the query, adaptive query execution on the top, is as soon as I started executing my query, I'm going to use this statistics to revise my plan and pick a better plan to execute. There's fair bit of variation on how a plan can change. AQE right now support 3 changes mid-execution. These changes will grow as we develop more and add more, and add smarts to make smarter decision. But those 3 changes are the one that you can see on the screen. We decide based on some of the statistics we should change a join strategy. We decide occasionally that we have to change a shuffle partition, and also automatically, if we see data skews, we'll apply anti-skew algorithms and we break it down, which I'll cover how it works. So those are the three specific changes that you can have: a plan that gets executed, and then gets changed, and the change is one of those three categories. But let's see what are those three categories and how basically I give you an example of how it works. So joins are expensive. There are different type of joins. I'll cover in a little bit further down, like the type of joins that we have. The most effective join is like the fastest version of join is a broadcast join, and the broadcast join essentially says, if let's look at just a two join table, very simple one. You have a big table, you have a small table that you want to join it. What you do, you pick up the small table, you send it to all of your distributed environments. So if you have 10 nodes or 5 nodes, the way that you saw in the previous presentation, the environment compute can be elastic, so you can go up to hundreds of nodes, and then each of those nodes, they'll have a copy of the small table, and they do the join basically locally on the same machine. So there is no shuffle, there is no network transfer, because just the small table, and that's very key. So when you're using broadcast join, the table that you're broadcasting and sending it to all the cluster nodes, it has to be small. And that's where the whole thing starts being tricky in the Spark 2.0. So you have to pick the threshold. I think the default is either 2 GB or 8 GB, but you could change it. You could change, okay, I want to broadcast my table because for some reason you're smarter than the Catalyst and the Query Planner and you know what you're doing. But again, it was really hard to tune it. It was hard to maintain it because the table sizes will change, and out of memory exceptions were those, like, it's the nightmare of every developer. And when you start working with broadcast join, that's something you start like tuning it and changing it, and you start thinking, okay, I'm going to make a decision on behalf of the Spark to do something. You will see lots of out of memory exceptions. But what happened here is you don't really have to define a broadcast join anymore. So on the left, there is an execution plan, which SMJ stands for sort merge join. It's a sort merge join, which you have written a join between two tables, left child and right child. When the plan was devised, we basically decided, okay, we're gonna do a sort merge join. Then you start executing. As soon as the execution starts, the adaptive query execution sees that, okay, my right table is actually pretty tiny. So instead of me doing a sort merge join, I'm gonna pick it up, broadcast it to all the nodes, and I'm gonna do a broadcast hash join. So that's how it decides on a size of a table. Another interesting bit of it is actually guessing the size of the data in memory is pretty tricky, because it doesn't really translate exactly one-to-one to the size of data that you have it stored on S3 or Azure storage or wherever that you have. So the AQE just decided, okay, this is better. It's better for me to do a broadcast hash join rather than a sort merge join. This was one of the items that we would do. Another one is around shuffles and shuffle partitions. Again, shuffle is, we refer to shuffle to any kind of data that needs to move across the network or needs to move from one of your compute node to another compute node, and also the number of partitions in the shuffle. The default value is 200. So if you typically open any random Spark notebook or a Spark jobs and just do not touch that variable and execute the job, you see the number of tasks is 200, and then it progress something out of 200. So that 200 is the default value, but it's pretty difficult to pick a right value and have it correct for the whole of your query. Typically, we would say that that number should be equal to number of cores that you have. So for instance, if your environment has 10 compute nodes, each of them have 64 core, you could go as up as 640 partitions, especially when you're dealing with big data sets. But again, when you set that number, it's going to stay through the session, and you can't basically, it's pretty tough to pick a number for part, like it's almost not possible to for part of your query. You can explicitly change it, but it comes with also some drawbacks. If it's too small, you have lots of it spill to the disk, because the amount of data per partition is going to be pretty big, and you're going to run out of memory. You have garbage collection pressure. If it's too hard, equally, you're going to have pressure on your scheduler, and the I/O wouldn't be very efficient because each of the partitions, that it's the big number, it's just reading very little data. And similar at the previous one, it's hard to actually maintain it and keep it up to date with your data as the data change kind of frequently. So AQE basically look at your data and optimize this. It decide, okay, you will set a value for your biggest data set, and then when the execution gets started, it does, depending, for instance, on the amount of data, it's going to go to from one stage to another stage. AQE decided, okay, I can actually reduce the number of partitions, so I have this process quicker, and I need less number of cores to process it, and it just helps you out of the box to reduce number of the partitions. The other thing that is just very frequent if you're dealing with a huge amount of data or any kind of data that has seasonality, it's data skew. So if you have a data skew in your data set, you will have these odd behaviors that there is a job that usually runs in 10 minutes, but for some specific month or specific days, it runs for hours and hours. You will see out of the 200 tasks that's running, 199 is finished in one. It's just waiting and it's executing. So you'll have very low utilization on the compute, and then you're basically waiting for one executor to finish its job. Lots of this explained. And there are different techniques to basically deal with this data skew, which before this you had to actually plan code it within your data pipeline. With AQE, we kind of give you a way that we look at your data, we can look at your data, we'll look at each partition. For example, you see now the partition A is a bigger size partition, is skewed, and we split that partition to two pieces, and then when you're joining it, we are duplicating the table that needs to be joined. So each of those splits will get a copy of the table that needs to join. So you don't really have to think about how do I solve data skew, and we apply anti-skew algorithm just out of the box. So these are the three items on AQE, but there are a couple of other things that I would like to cover. I think this is again an interesting one. There is a concept called dynamic partition pruning. So a static partition pruning is pretty much a fancy name for not reading files and folders from your cloud storage. So if you see on the far left, you have a basic data flow, which you read all of your data, you scan everything, and you filter, for instance, a store ID equal to 5. In the one that does the filter and do the scan, we assume that the data is actually partitioned by a store ID, and that partitioning means that the data on the disk is stored by, for instance, a subfolder store ID equal 5, subfolder store ID equal 6. So when you're executing a where condition with that, the planner knows that it just needs to go and read that subfolder. It doesn't touch any other folders. This is also true if you do multi-column partitioning. So if you're partitioning based on, for instance, year, month, and store ID, if you have a query that says store ID equal 5, basically Spark goes to every subfolder, just pick up the store ID equal 5 and bring it back. If you add more into the where condition, for instance, year equal 2020 and month equal to 7, then it knows exactly which subfolder it has to go, and it basically ignores all the other data in the storage. So it doesn't matter whether you have 1 million row, 100 million rows. A good partitioning strategy is priceless. But that's basically static, right? So you can't possibly know all of your query pattern, all of the partitioning strategy, and that's usually happens when you have you can query one table. But if you start joining things, as Graham said, most of the data warehousing, most of the big data processing tools, they prefer a very wide pre-joined denormalized table, but it doesn't mean that's the only way to do it, and no one can basically denormalize everything they have. That's the extra level of ETLing to a denormalized table and maintaining an extra step in your ETL pipeline. But if you look at typical star schema queries is I'm joining a large fact table, which is my sales transaction table, to a dimensional table, which it's probably pretty tiny. And I'm just going to look for all the transactions, sales transaction from City of New York. So in this scenario, the actual partitioning on the large table doesn't have the city ID, because the city ID is kind of the join key here, but the partition sits on the small table. Even though if we can do a static partition pruning, it's not going to help a lot because it's a small table and we read a smaller subset of that table. You still have to get the big table and basically start doing sort merge or hash join partition joins, and that's pretty expensive. With again, as usual, I present this yesterday and I covered this slide even yesterday before its turn. That's what we just talked about. So you can denormalize it, and you can actually, when you're storing that denormalized table, you can now partition it based on the city, and then that would basically benefit from static partition pruning. But if you look at the dynamic partition pruning, what happens as soon as you start the query, what this Spark does is go to the small table, scan the dimension table here, and start picking up basically the filters that you required for your join, and start broadcasting those filters to the bigger table. So now that you are scanning the bigger table, but you already know what you're going to join it on. So a smaller subset of that fact table, that super big table, gets to the hash join. So you're trying to eliminate as many records as you can before you get to the join and start comparing. Like you have a build side and you have a compare side, and you start doing your hash join. You try to eliminate as many rows as you can, and using the dynamic partition pruning, we basically pick up the filters, we distribute it across all the compute nodes and say, hey, whatever row you're going to bring up and use in a join, it has to match these criteria. So if they don't, just like don't bring it up, because there might be other conditions in your var also. It's not just city equal to New York, but if we know there is a city equal to New York, and then there is a city equal to, I don't know, California, then that row doesn't really have to come up because it's not going to come out of our join anyway. A sample workload comparison. So if you have the dynamic partition pruning on, and just you run it on a TPC-DS queries, those are the query numbers, and that's the percentage on the y-axis. That's the percentage performance gain that you get. So just having it, turning it on, you basically read as only the data that you need, and you try to minimize reading the data you don't need, and that's the percentage that you gain from the query speed and speed up. I'm gonna cover this a bit faster. So in Spark 2.x, we had different kind of hints. A hint is basically when, as the name suggests, you are telling the Spark execution and the Spark planner that, hey, I'm giving you a hint. I know how to join this. So I think we had the broadcast. We had the range join hint and a broadcast hint in the Spark 2.x, but now we have added shuffle, hash, sort, merge, and Cartesian product. This is basically for the expert level users that they kind of know the query that they're writing. They know their data set very, very well. They know the join strategies really well. And they say, okay, instead of leaving it to Spark to make a decision for me, I'm going to tell Spark how to join it for me. There's different, basically, benefits and different speed performance to each of those join. Like for instance, the sort merge is the most robust one, can handle any size of data, but it needs shuffle because it does sorting. Then broadcast hash is another sort that it's very fast, it's very local. You send it to the basically you send the build side to all the nodes in the compute, and then you can kind of do everything locally. And then you have shuffle hash and shuffle nested loop, which they have their own benefits, and there are different times that use any of those things. As I said, this is not really for even intermediate and advanced user, you really have to be in expert zone to start looking at your DAG, your query plan, the cost, and the optimizer, and deciding, okay, I'm smarter than the Spark execution and the planner, and I'm going to pick my own join strategy. And how do we use it? It's basically looks like comment. If you see if within the SQL, you just say shuffle merge, and this execute the shuffle merge join instead of thinking at what's the best, applying the rules and the cost. It basically throw those things out and just listen to the user and do a shuffle merge join. Usability, that's my favorite part. So if you've used a Spark, at some point you have started looking at the explain plans, or even if you're not using Spark, you're using any kind of a SQL. There is an explain plan, different version of a different syntax, but this is what it looked like in the old plan in a 2.x. It was, I think it was supposed to be very smart and show you each of those stages and how we go from one to other, but it was really hard to read, especially if you had subqueries and you had aliases and you had CTEs. It was really difficult to read this. And what we have done in the Spark 3.0 is we have basically split in two sections. There's a header, which looks like an index. It just gives you what I've done. Very, very simple, very quick. So yeah, like the one that you can see on my screen, it shows that I've scanned Parquet, I've done some filtering, I've done a hash aggregate, that exchange is shuffling, and then I have done another hash aggregate and a filter. And then you can correlate each of those numbers to individual sections in the footer. So you know the scan Parquet, I have basically read a file that sits here called loans Parquet. I've selected loan ID and funded amount. It was a batch. I push this partition out, and then you can go to the next one, So it gives you an easy way to digest what's happening. And the best part is it has a dedicated section for subqueries. So you can actually look at your subquery and say, okay, these are the number of subqueries I have. And you can start, if you really want to optimize your query, you can start from slowest part and then optimize one subquery, see what's happening there, what's going out, what's being used in an outer query, and then moving forward. And there's more to come. So we are still working on this to make this even add the cost correlated with the SQL command, correlated with the actual Spark stage, because if you see in a Spark UI, there is a stage there, and we can actually see each of those core SQL sections, how it's correlated to the each stage of the job in the Spark. If you're into streaming and you're doing streaming, you now have a structured streaming tab. Well, Databricks Notebook had this built in, but now the open source version also have the structured streaming tab, which you can start looking at some graphs. It gives you a 2 minutes rolling window of what's the streaming process look like, from input rates, process rates, what are you processing, what's the batch duration. So if you want to see how you can optimize it, what's the SLA that you're hitting, and what do you have to tune to get to where you want, that's some graphs that you can get just out of the box, and it's really handy to look at your streaming jobs. Then we go about UDFs. As I said, one of the issues was basically, this is the history of how the UDFs were introduced. So they came along somewhere in 2013, 14. They were pretty bad. I think that would be the understatement of the century. It was row by row operation. So if you were adding like one to one column, it was just going to go through individual row and add it. It was very expensive. Pretty much up to Spark 2.3, 2.4, which we added pandas UDFs, and we started using Arrow as a serialization, and all the functions now were vectorized. So instead of doing row by row operation, it was doing a vectorized operation. That was weird that you get like 100x performance improvement over the normal row by row operations. And that's where you start using pandas, but it wasn't really Pythonic. So if you look at a side-by-side comparison of how did this look like in 2.3 compared to Spark 3, you see, like, if you look at the one on top, you had to remember the function tab. You didn't know what you have to pass, right? But now now you can start using Python hints, and very easily you can define your function. You know what's the input, what's the output. It doesn't really it hasn't changed the performance perspective. It still uses arrows, still vectorized, but it's just easier to use to look at it and understand what's happening and what type of input output goes to this function. I think I have 2 more slides. So if you are using Spark 2.x and you want to jump in 3x, you can only build with a Scala 2.12. So 2.11 before, you can't use it anymore. Python 2 depreciated in a Spark 3, but it was end of life anyway in I think January-ish. So you have to go with Scala 2.12 and Python 3. If you have other dependencies like Hadoop and Hive dependencies, those are the version that you need to build and the Java version in there. And the method store that you have, it pretty much support all of the latest version that you would see in production. And you could build with any of those versions. I don't know how I'm on for time, but let me just show you a couple of other things. If you are using any of the functionalities that you think you have missed and depreciated, you can use spark.sql.legacy to bring back those functionality and use those settings. Most of them that works. Just it is there is a small comparison table in Spark ML and how some of those methods has changed or depreciated and how it's being used from input output perspective. So you can look at this. I'm sure if you have a code, as soon as you upgrade your Maven or SPT or whatever you're using for your build, you're going to see those mismatches, but this is something that they'll put together in advance. If you're using R and Spark, then there's a set of things that has been depreciated and replaced with new methods. And yeah, last not least, there are a couple of other open source projects that I think it's worth having a look. Not a big fan of this build. If you're Panda users and you don't know what the Spark is, you actually don't need to know what Spark is. You can continue using Pandas, and there's a project called Quotas, check it out, that basically pick up your Panda code as it is without change and run it on the Spark. There is another open source project called Delta Lake. So if you are building or thinking to build a data lake, there are a set of challenges that you have to face, you will face, typically because the cloud storages are cheap and dumb, but you need something more intelligent, like you need transaction, you need the schema enforcement, you need indexes, you need performance. That's something that Delta Lake gives you, building a lake on either an S3 or Azure storage and other clouds to come. Check those 2 out. I think one more, I'm going to call it out. Check Redash also. It's one of the visualization tools that we have started to integrate very neatly into our product. So you will see some announcement. I think there was an announcement that we actually acquired Redash as a company, and we're going to build Redash into the Spark. And so you can use Redash as a SQL kind of a workbench environment to purely write SQL if you are not a Python or Scala or Java user. Well, actually, no one can write Java on Spark anymore, but you can use Redash as your SQL management studio type of view that just run SQLs and do visualization using your SQL. That would be me. I don't know how our time, but I'm happy to take some questions. If there is any.
Oh yeah, there's about 4 questions at least. Peter, did you want to moderate through the questions?
Either way, you want to take them?
That's good. Can I firstly say that was awesome. I learned so much in a short length of time, so I've got to replay that to cover it all. So I'm going to answer the first question from the Q&A bit. So Najah asked, thanks, Mahdi. Nice prezzo. Would love to know your thoughts and experiences around the Kubernetes operator with Spark 3.0.
I have very little experience with the Spark 3.0 and specifically non-Databricks related Kubernetes operator. I'm working with, working is a bit of an overstatement. I think she has done the chunk of the job. But there is a Databricks operator written for Azure Databricks operator, written by a couple of Microsoft employees that are actually based in Australia. I'm working with them to see how we can basically pick it up and promote it and make it basically more publicly usable and get people to use it. I definitely see value in them. I haven't really figured out where would they best fit. Like, again, I have a limited experience with them, but in my mind, like if you start looking at, for instance, again, Databricks perspective, anything you see our environments is API driven. So you can spin up environments, auto scale environment, completely transparently managed by us, run a code that scale from 5 nodes to the hundreds of nodes, and run a bunch of Spark commands, and you never know what's happening on the infrastructure side. So we abstract away your cloud provider, whether you're on Azure or on AWS. So we have done a fair bit on our side already to abstract away the infrastructure and let you concentrate on the actual logic and code that you write. I don't know whether I'm going to use them for like an ARM template Terraform kind of a mix. I still haven't figured out where to use them and what's the actual niche that they're being used for, but that's probably more my fault than I'm sure there is a use for them somewhere. Sorry, that was probably the answer not you expecting.
No, that's good. It's also good background as well. Got a question from Claudia asking, do you know if there's deep reinforcing learning research into Spark to optimize the execution plan? Or maybe that's a feature for Spark 4.0.
If there is, sorry, what? Deep learning.
Deep reinforcement learning research into Spark to optimize the execution plan. So I think this is a question about whether reinforcement learning can be used to improve the execution plan.
No, I definitely have seen papers on it. And if someone going to add it to the execution plan, it's probably going to be Databricks, but I can tell you we're not working at like it. It's not on top of our list. It definitely makes sense. You know, let's start learning from the plan that you have executed many, many times and come up with a smarter plan. I don't know whether that like as the AQE gets advanced and have more and a smarter decision to make, would any of those decisions start being more heuristic and start looking at the previous execution plans and we store statistics for the previous runs and learn from those previous runs and like optimize the plan to that level? I don't know. I think there is a fair bit of work to get there.
Okay. Between now and next Spark Summit, just throw that in. We've got a question from Aditha. If AQE can dynamically decide partitions, can we expect the same number of tasks and part files every time the same query is run? So I'm guessing that's a question is it deterministic? So if AQE can dynamically decide partitions, can we expect the same number of tasks and part files every time the same query is run?
If you run it on a stale data, yes. But if your data changes, you probably, your number of partitions might change. So for instance, if you're like AQE will decide to do a broadcast hash join instead of sort merge join, if the data, the right-hand side of your joins is small. So if that data size changes, and when you're running it now, it decides, well, it makes sense to broadcast 1 gigabyte of data. But then when you're running it 2 months later, that table that was small to be broadcasted is not small anymore. So it goes through this sort merge joins, and you will end up having 2 different plans for the same query across 2 different times. I don't have the UI, but the Spark UI clearly shows you that, okay, I decided to make a decision and it's the AQE kicking in and changing the plan. So you can see it. And if you have the 2 queries on side by side, you can actually see why AQE decided to do a hash join, a broadcast join on one, and then went to a sort merge join another time. So if the data is stale or doesn't statistically change, significantly change, that the decision tree still says, okay, do the same thing, it will do the same thing.
Yep. Oh, that's cool. Not a question. Raymond just gave thumbs up to koalas and said it's super good for panda nerds like me who have no clue about Spark. So yay Yay for abstractions. Peter, could you find any additional questions on Slack or Twitch? Sorry, I haven't been following that one.
No, we're all good. I think we can probably wrap it up. Did you want me to share a slide or something?
Yeah, bring us home, Peter.
Awesome. Hopefully my slides are sharing, are they? Yeah. Cool. Well, thank you so much again, obviously, to our awesome host, Simon Aubrey, Principal Data Engineer at ThoughtWorks. We had Mahdi Askari from Databricks and Graham Polley from, he's wearing his community hat as a bit of a developer advocate for GCP tonight, but he also works at Servian, so really good chap. Thanks so much for taking us through, lessons learned. That's always good. As always, you can sort of catch up with stuff on Data Engineers Meetup Slack group, and also we've got a Twitch channel, and we've been promoting our YouTube channel. So if you didn't catch everything tonight, you'll be able to catch up on the videos there. Just remember, dataengconf.com.au. We've kind of slightly rebranded as DataEngBytes. We're not professional marketers, we're data engineers. That's why we don't have a matching URL to the name of the conference. Remember that. But anyway, thanks so much, and see you at the next meetup. Stay tuned. Cheers. Bye-bye.
Thanks all.
Bye.
Bye.
Bye.